So we'll be continuing with module number 4, the modulators, or specifically the optical modulators. And today we are going to look at another special kind of optical modulators called as acoustic optical modulators. So the main objective of this class is to understand the acousto-optic effect and acousto-optic modulation. Okay, and then we'll look at specifically the Raman-Nath modulation and the Bragg modulation. So acoustics is something you might have already heard of, the acoustic waves, like the waves traveling in the water, or a sound wave is all acoustic waves. It is not like the normal electromagnetic wave, but it's kind of a wave which propagates. Okay, so when this wave propagates through some materials, and if light is incident on these materials, then there is some changes happening to the light or the optical signal. And because of this change, we can basically modulate, change the some parameters of this optical signal by providing or by changing the acoustic signal. So this is called as the acoustic modulation. So the acousto-optic effect is the change in the refractive index of a medium caused by the mechanical strains accompanying the passage of an acoustic wave through the medium. Okay, we have seen in electro-optic effect that when you apply a voltage, the refractive index is changed. Instead, in acousto-optic effect, we are applying some mechanical strain because of which there is some waveform which is generated on the medium or the material, and this change will result in changing the refractive index of the material. We'll see more detail. Okay? The strain and hence the refractive index varies periodically with the wavelength lambda. Okay, so if lambda is the wavelength or the some pattern in which the wave, the acoustic wave, is propagating through the medium, now depending on that wavelength, the refractive index will also get changed. Okay, so to illustrate how that effect happens, so this is the material which shows the acousto-optic effect. Okay, and you're providing the acoustic waves along this direction. You're providing the optical waves along this direction. So you see that both are normal to each other. Okay. Now you have something called as a wave front. So what is a wave front? So wave front you can define as if you track any particular phase of the wave, then that is called as a wave front. For example, let's say this is a sine wave. Okay. Now I am saying that I'm going to track the maximum of the sine wave, which is basically this. So there is a plane I can draw here. Sorry. I can draw a plane here along which the maxima occurs. So the next plane will come here. Next plane will come here. Basically, I'm tracking a particular phase, which is currently in this case the maxima of the wave. Okay, so each of this plane represents the point at which your wave has a maximum. Now remember, it need not be a maximum, it can be any point on the wave. So this is called as a wave front. The front of the wave, the path of the wave. Okay, so if you look this wave from front along this direction, let's say if you're looking from here, you see the straight line. There's a straight line here, there's a straight line here, there's a straight line here. which is shown in here. So this is wavefronts of the acoustic wave, and this is the wavefronts of the optical wave. And similarly, if you look at the distance between the wavefronts, it is basically lambda, because you are measuring the maxima of the wave, and two maximas, the length of difference between the two maximas is actually your wavelength. So this actually gives the lambda. Okay. So acoustic waves is traveling in this direction. So there are multiple lines drawn here. Some are dashed, or some are like thick, and we'll see what all these things are. And we are going to see how it changes things. Okay. So a monochromatic wave of wavelength lambda, which is this one, which is an optical wave, is incident upon a medium in which an acoustic wave has produced sinusoidal variations of wavelength lambda in the refractive index. So as this acoustic wave is propagating, now when the wave propagates, at some points it will have maximum, and at some points it will have minimum. Okay. So whenever there is minimum, you have a minimum refractive index, and wherever there is maximum, you have a maximum refractive index because of propagation of acoustic waves. And this will produce change in refractive index, and change in refractive index is directly proportional to the wavelength, because wherever, so not the wavelength, the amplitude of acoustic. So wherever you have maximum, you will have maximum refractive index. Wherever you have minimum, you have minimum refractive index. So basically it follows some kind of a wavelength. Okay. So the solid horizontal lines represents acoustic wave peaks or pressure maxima, and the dashed horizontal lines represent acoustic wave troughs or pressure minima. So in this one, this solid lines actually represents the acoustic wave peak. Okay. So actually you should look from this direction. So this is the peak. Okay. So also this is the peak, this is the peak. So those are all different wavefronts where you can see it is the peak. Okay. Now the dashed lines, which is this, is actually the trough or the minimum. So this is another trough, and you can see another trough comes here. Okay. So the solid lines is the peak, and the dashed lines is the trough. Okay. Fine. Now, as the wave enters the medium, the portions of the wavefront near to pressure peak will encounter a higher refractive index and therefore advance with lower velocity than those portions of the wavefront which encounter pressure minima. So your optical wave is coming like this with the wavefront. Okay, so assume that these are all like the portions where you have maxima for optical wave. Now as it reaches this medium here, some portions, for example, these portions along this will experience minimum, sorry, maxima. These portions will experience minima. Okay, and these portions again maxima, minima, maxima, etc. Actually, all these portions in between minima and maxima will also experience a change in refractive index, because the acoustic wave has a different amplitude. So before reaching this medium, all these wavefronts have maximum, all these have maximum, but after coming out of, after the medium, it will have a variation something like this. Okay, and the wavelength is now proportional to the wavelength of the acoustic wave, which is lambda. Thus, the incident optical wave, which has some particular wavelength, has been changed. So wherever the refractive index is maximum, you know that your velocity will be minimum. And wherever the refractive index is minimum, you know the velocity will be maximum. So there is a change in velocity because of this change in refractive index, which in turn will change the wavelength. So thus the modulation has happened. So the optical wave with a particular wavelength or a particular velocity has changed its wavelength and velocity at different wavefronts. Okay, so the wavefront in the medium therefore soon acquires the wavy appearance as shown by the dashed curve. So dashed curve shows you how the wavelength has changed. Okay, so this is the basic of Acousto optic effect, and we are going to see two such modulators. One is called as Raman-Nath, another is Bragg, and those are based on something called as Raman-Nath regime and Bragg regime. Okay, so the light diffracted by an acoustic wave of a single frequency produces two distinct diffraction types. Okay, and these are Raman-Nath diffraction and Bragg diffraction, or Raman-Nath regime and Bragg regime. So there's an N here. Okay, so what does it mean? So there's an acoustic wave which is supplied to this material, and an optical wave also supplied to this material. The wavefronts are shown in this material. In Raman-Nath diffraction, once the wave enters the medium where there is a change in acoustic material, then it will diffract after incidentting on this wavefront. And the diffraction occurs with different modes. So diffraction is not a single diffraction. It will get split into multiple orders. So this is called as orders. There's a number here which is called as an order. So this is zero order, which is going straight. This is the first order, which is going the first one after the straight one, and goes on like that. Okay. Fine. Now, there's a parameter called as quality factor Q, which says whether it is a Bragg diffraction or a Raman-Nath diffraction. So in Bragg diffraction, if it is incident normally or some angle theta, it will get split only into two orders, the first order and the zero order. There won't be any multiple orders. But the important thing here to note is that the length L for Raman-Nath regime is very small, and the length L for Bragg diffraction is very large. Okay. So there's a parameter called as quality factor Q. It says whether it is which regime. Okay, and this is the equation which gives the quality factor Q. So this equation is just for your reference. Okay, so this is the Raman-Nath regime. The light is incident roughly normal to the acoustic beam, and there are several diffraction orders: -2, -1, 0, 1, 2, 3. It is given here with intensities given by Bessel functions. Okay. For Raman-Nath order, your value of Q is much less than 1. I think I haven't specified it here. Much less than 1. Because the value of L is very small, and it will get split into multiple diffraction patterns. In Bragg diffraction, at one particular incidence angle, that is theta b, only one diffraction order is produced. Okay. The others are annihilated by destructive interference. So basically, the zeroth order is basically your normal wave, and the first order is the only diffraction that is being produced. All other, so basically inside this material, there are many diffractions happening. Okay, but all the diffractions are cancelled out once it reaches the outside of the material because of the destructive interference. So these are two different regimes in optical scenario. So if you come to Raman-Nath modulator, the main property of Raman-Nath modulator or the regime is the acoustic diffraction grating is so thin that the diffracted light suffers no further redistribution before leaving the modulator. Okay, so the Raman-Nath modulator has a very thin grating. Okay, it's very thin, so that when the light is incident, let's say it is normally incident, it will not have enough time to do any kind of constructive or destructive interference within this grating. So the diffracted light will directly come out. Okay, and each of this diffracted light is given a number which is called as an order. So this is 0, this is -1, +1, +2, etc. Okay, the light is diffracted as from a simple plane grating such that m lambda 0 is capital lambda sine theta, where m is called as the order, which takes a value like this. Theta m is the angle of diffraction, and lambda is basically the incident wavelength, and capital lambda is the wavelength of the acoustic wave. Okay, so this is the condition, or this is the equation which governs Raman-Nath modulator. So if you come to the structure of a Raman-Nath modulator, you see that you have a this is very small, this length L. The incident beam is incident normally. You have a piezoelectric transducer, okay, which creates an acoustic wave. And you see there are wave fronts. These are all wave fronts. Okay. Now, because of this wave front, there will be change in refractive index. So as the as the incident beam travels through this material, it will get diffracted in multiple ways because of the Raman-Nath diffraction. Okay, it can be diffracted in all, so that if there are multiple beams, it will all get diffracted, and each has an order. Now, what we will do is we will use a lens to focus into one particular point. We will try to focus, and we will have a small slit such that it will pass only the zeroth order. Okay, because we don't want all other multiple orders. We want only the zeroth order because that is the one which gives me the incident beam. Okay, so remember, when all these mth order are coming out, they have a different velocity or a different wavelength. Okay, and only the order which is coming out directly without any diffraction is the one which we need, which is this one. And we use a small slit such that all other orders will get filtered out, and you will get only the zeroth order. And zeroth order beam will be modulated with a different frequency, sorry, different wavelength or a different velocity. Okay, that's how the modulation is happening. The irradiance I of the light in the orders depends on ruling depth of acoustic grating, which is related to the amplitude of acoustic grating. Irradiance means the intensity, basically. It depends on the depth. Depth means the size of the material of the acoustic grating, which is we have seen it is L, which is related to the amplitude. Okay, the amplitude of the acoustic grating is related to the amplitude of acoustic modulating wave. So the modulating wave will change the refractive index, which in turn changes the amplitude of acoustic grating. A slit which allows only zero order beam is placed. The fraction of light removed from the zero order beam is eta is equal to I0 minus I by I0, where I0 is the transmitted irradiance in the absence of acoustic wave. So if you have the material and if you incident light without giving any acoustic signal, it will produce you a zeroth order beam of wave with some intensity. Now, if you compare that with the same material giving an acoustic, provided with an acoustic wave, incident with an optical wave, and zeroth order wave coming out, what is the relation between, or how much amount of the intensity is available when compared to a non-acoustic provided acoustic wave provided material. So that is basically the efficiency. Okay, thus amplitude variations of acoustic wave are transformed into irradiance variations of optical wave. So by changing the amplitude, actually the wavelength is changed, also the intensity is also changed. That is Raman-Nath modulator. Next is Bragg modulator. So in Bragg modulator, the acoustic wave frequency is high and the acousto-optic interaction length Q is much greater than 1. So one thing that I forgot to mention in Raman-Nath modulator is here the acoustic frequency is low. Okay, but in Bragg modulator you have a high acoustic frequency. The physical basis of Bragg regime is that the light diffracted from the incident beam is extensively re-diffracted before leaving the acoustic field. We will see a diagram in which we will see how that happens. What it says is, if this is a material, the wave is incident, let's say some angle, okay, and there is a diffraction, too much of diffraction happening, such that only those waves in which there is a constructive interference will come out. So there is an extensively diffraction before leaving the acoustic field. So under these conditions, the acoustic field acts very much like a thick diffraction grating, that is, a grating made up of planes rather than lines. So when you just resize this, you can say that there is a big plane here inside the grating in which there is some kind of multiple diffractions happening. Okay, we'll see the figure. So this figure illustrates what we have said. So these are basically the wave fronts. Okay, and they are big. Wave fronts means this is called wave, and there is a change in refractive index. So whenever there is a change in refractive index, there is some kind of reflection. So the wave is incident at theta I, and it is reflected at some angle theta d. Okay. Now, so the wave grating planes at an angle of incidence theta I, significant amounts of light will emerge only in those directions in which there is a constructive interference occurs. That is, which satisfies the first condition. Light scattered from a given grating plane must arrive in phase at the new wavefront. So for example, if you look at this one, and if you travel to this one, if you take any wavefront, that should be in phase. So here you take a wavefront here, this your wave might have the maxima here, then you should have the same maxima here. Sorry. Okay, that means they are in phase. Second condition is light scattered from successive grating planes must also arrive in phase at the new wavefront, implying that the path difference must be an integral number of wavelengths. So you see there is another wave which is incident here and coming to the same wavefront. Okay, if the phase difference between this and this wave is same, there is a constructive interference. Otherwise, there is destructive interference. If it is a destructive interference, these waves will cancel out. The energy will be lost. If there is a constructive interference, it will get added up and it will finally emerge out of the material. Okay. So the first condition is satisfied if theta d is equal to theta I. So if the angle of incident and angle of diffraction is same, then for the same wave, the phase difference after diffraction will be same. Okay, so that is this. The phase difference after diffraction will be same if theta I is equal to theta d. The second condition requires that sine theta I plus sine theta d is equal to m lambda by lambda, where lambda is the incident wavelength of the incident optical wave, and capital lambda is the wavelength of acoustic wave. So if this condition is satisfied, then any two adjacent waves which has reflected, for example these two waves, will give a constructive interference at the wave, which is basically the second condition. If you combine these conditions, then the condition, if it satisfies, if it is this, then there is constructive interference at successive waves and also for the same wave. Okay? This is a condition which should be satisfied for the wave to have constructive interference. So in Bragg modulator, this is a situation. So you have multiple planes here. The incident beam is coming. Actually, this should have come like this with a zero order without reflection, but it will get diffracted and go as a first order. Okay. Now, the equation for Bragg angle then becomes sine theta b is equal to lambda by 2 lambda. Now, what is a Bragg angle? The Bragg angle is the angle at which there is a constructive interference. Okay. So if theta b is just satisfies lambda by 2 capital lambda, then there will be a constructive interference for the incident beam. Okay, and there's a big derivation for Bragg angle, as actually it is 2d sine theta is equal to n lambda and you see that sine theta is equal to n lambda by 2d, where d is the distance between any two wavefronts. So d is here capital lambda. That's how you can derive that. Okay, so this is a Bragg's law is there from which you can derive. But the important thing here is the modulation depth or the diffraction efficiency is almost 100%. While Raman-Nath has this efficiency around 34 to 35%, which is very low. So you can say that almost all the incident beam will get modulated and get diffracted and comes outside. Okay. And at Bragg angle, that is at theta b, the efficiency is eta is equal to sine square phi by 2, where phi is given by this equation. Okay, this is for your reference. Just for the completeness, I'm saying the equation. Okay, so delta n is the amplitude of refractive index, L is the length of modulator. Okay. Now there is a frequency shift in this Bragg modulation. Why there is a frequency shift? Because of Doppler effect. Now, Doppler effect is the effect in which if there is a relative motion between the source and the destination, then the destination will see a change in frequency. That is basically the Doppler effect. Okay. So why Doppler effect is happening? You see there is wavefronts in the Bragg modulator. Actually, these wavefronts are moving, right? Because this is basically an acoustic wave. Okay, and the wavefronts are moving with some good amount of speed because the frequency is high. In Raman-Nath, the frequency is low, because of which the wavefronts will be moving at a bit of a lower speed. Since the frequency is high, it might have a higher speed or a higher velocity. Now, because it has higher velocity, when the wave is incident on this wavefront, there, because of a change in refractive index, it will get diffracted. Okay, so you see there is a change in relative motion because this wavefront is keeping on moving. This wavefront keeps on moving. So if you take any two waves, there is, or if you take the incident wave and the diffracted wave, there is a change in relative motion. there is a relative motion because of the change in refractive index, which is higher in the higher level because of the change in acoustic wave frequency. Okay, this causes a Doppler effect, and the new frequency is given by nu dash is equal to nu 0 into 1 plus or minus 2 nu a c by n, where plus or minus nu a is the component of velocity of the acoustic wave along the original beam direction. Okay, so if this acoustic wave has along this direction some component, that is nu a, and the frequency shift is basically nu dash minus nu 0. So if you take nu 0 to this side, you will get this expression. Okay, and so this I am saying about normal incidence, and if the incident angle is theta d, then it can be modified by including sine theta. Okay, so basically what I am saying is, by changing the frequency of the acoustic wave, you can change the frequency of the incident wave, which is some kind of a modulation. This means this change in frequency can be used as the basis of frequency modulator. So the frequency of the diffracted wave can be changed by changing the frequency of acoustic wave, so that the output will have different frequency when compared to the incident wave. Okay, so that is regarding the Bragg modulator. Okay, so this is a small topic, which is acoustic modulator modulation, which I hope you have understood. Okay, yeah, so I think we are done with today.